Okay, should be recording. So let me hand things over to group one. And as I said to the panel, I'll send you guys the rubric here in just a second.
Awesome. Thank you, Dr. Trom. Well, first of all, I'd like to start off by, on behalf of Evil Inc., our company, welcome each and every one of you guys who have joined our presentation as we present our canisterized satellite dispenser design called Jack in the Box. So we're group one, which consists of Zachary Hole, Alejandro Navarrete, Zain Omar, John Parker, Sridhar Shanbag, and Asher Siddiqui. So just a brief agenda over what we're going to be covering today. We're going to start off with a brief overview about our company and our values, jump into our product overview, and then really dive into each subsystem. From there, we'll highlight some features, go over some cost estimates, and then finish it off with a conclusion. So as a company, Evil Inc. brings a diverse group of engineers together. So what really we bring to the table is a cohesive and synergetic team with industry, design team, and research experience, all totaling a cumulative 15 years of design and manufacturing experience. Our passion stems from our desire to bring an innovative and reliable product to the market that maintains high quality and efficiency standards. We really value the safety of the mission and the safety of the environment. So all parts of the product mission, they were addressed without contamination of lunar orbit or any other public health threats. Our company's economic engine is to maximize profit per consumer. And that's important in this industry due to the limited customer base and the specialized product. And by lowering these production material costs, we're able to increase our margins. So we designed the Jack in the Box CSD to sort of encompass all three of these facets of our company goal to deliver a CSD that aligns with all the mission requirements while making our design competitive in the aerospace industry. So our design of this CSD, just a quick overview, was based off of a CubeSat design with global dimensions given by the aero design team of about 23 by 23 by 36 centimeters. And the global dimensions of our CSD are about 26 by 28 by 49 centimeters, with a total mass of 4.8 kilograms. The design features a monopiece aluminum shell, which houses a one spring dispensing system that launches the CubeSat at 1.9 meters per second, and an aluminum torsional spring door with a latch holds the CubeSat in the CSD until it's ready to launch. And then when it is ready, a burn wire release mechanism is used to unhook the latch, which releases the CubeSat. All communication and power components are held in the infrastructure panel in the back, which you can see in the back there, and that houses a Raspberry Pi and patch antenna, and some batteries that communicate information during the mission, and also help power the communication system. So we'll dive into each of the subsystems that I kind of give an overview of, but these are our 4 subsystems. So we have the enclosure and mounting system, opening door, dispenser, and infrastructure, which consists of communication and power. So I'm going to hand it off to Alejandro, who's going to discuss the enclosure and mounting subsystem.
Thank you, Zain. Okay, so this first section is going to talk about the enclosure and mounting subsystem of the CSD. The general goal for this subsystem is to house the CubeSat, to serve as the main and only mounting mechanism to the SLS, to have access points for assembling, maintenance, or any labor needed inside of the CSD. This, of course, after the CubeSat has been installed, and not to forget that we also want to provide protection to the payload, or to the CubeSat in this case. The enclosure and mounting subsystem are composed of 3 parts: the enclosure, which is the one that you can see on the left side, the removable plates, that is the one that you can see on the right side, and it has a cable management panel that goes on top of the enclosure. The cable management panel is used as a cosmetic component to enclose the tables around the CSD's locking mechanism. The removable plates function is to be the access point within the CSD to do any labor maintenance or assembling tasks inside of the CSD. These plates have a dimension of 17.57 times by 7.50 centimeters and a thickness of 0.50 millimeters, which is just, we're talking about sheet metal measurements. And lastly, the enclosure, again, which is the one on the left or the center, acts as the main component that sorts or houses the CubeSat, protects the payload, and serves as the mounting mechanism to the SLS. Just to repeat again, the mounting mechanism is part of the whole enclosure, right? So it's within the design. The enclosure is, as how Zane said it, the enclosure is designed as a monopiece shell with a global size of 25.30 by 25.30 by 43 centimeters. And since it has very specific geometry, we have a minimum thickness of 1.5 millimeters and maximum thickness of 10 millimeters. All the parts are made from aluminum 6061 T6, excluding the off-the-shelf components, which are the ones that are just the fasteners, basically. This subsystem uses a thermal protection coating, which is made from solar white, which has NASA flight heritage, and it's just the coating protection to the enclosure. There were several metrics, right, that we had to analyze, and one of those was the weight and volume capability. So just before talking about the weight and volume capability, I wanted to talk about a little bit more about manufacturing. The way the enclosure is going to be manufactured is going to be basically just an aluminum block where its intersection is going to be removed using EDM wire, and each face is going to be CNC. This is just going to achieve really high tolerances. Going back to the point of the weight and volume capabilities, the required payload volume is 22.6 by 36 centimeters, which is just the volume of a general CubeSat, in which our enclosure has an internal volume of 23 by 23 by 43 centimeters, which it provides an 80% of volume to be able to fit the CubeSat, and then the rest, which is the 20%, is just for the spring. Accounting for all the components in the enclosure, the subsystem has a total mass of 2.9 kilograms, which comes out to be around 58% of the total CSD weight, and complies with our requirement metric to be less or equal of 60% of the total weight of the CSD. As how I said before, several other metrics were analyzed to ensure the feasibility of the design, of course, at worst case scenarios. The second analyzed metric was the steady state load analysis, which it was done on of a 30 kilogram mass under 10 Gs in the enclosure. The 30 kilograms comes from the fact that the assumption that the CSD weighs 5 kilograms and the CubeSat weighs 25 kilograms. So that's where the 30 kilograms comes from. And this analysis was performed by calculating its yielding and buckling failure at a steady state loads. As you can see here, I'm just gonna give a very specific explanation of the process that I did to find the yielding factor and the buckling factor. As you can see, I mean, just the yielding factor is very straightforward. It's just the load over the area. The assumption that we took in this case was that we took it as the minimum thickness, as just like as a squared hollow beam, and we took it as the minimum thickness that we have in our current design, which is 1.3 millimeters, if I'm not wrong. And that was basically just the thickness that we used just to calculate the overall the overall stress. In this case, of course, the load is 30 kilonewtons because it's under 10 Gs, right? So it's 30 kilograms times the acceleration, which is 1,000 meters per second square. And that led to a 214.78 megapascals, which led to a 1.285 factor of safety, which was pretty good in this case. For our buckling failure, it was, again, pretty straightforward, just using a buckling failure load, and where you use just the elastic modulus, moment of inertia, and then the total length of the enclosure. And this was a little more, it was a higher factor of safety, right? In this case, it led to 1,546.8, which it complies with this metric. The third analysis, the third analyzed metric was the shock load analysis, which was evaluated at 800 to 8,000 hertz. This was a relationship that we got from the SLS documentation, and this was also a pretty straightforward analysis that we did. We modeled the enclosure, just the enclosure, as a basic excitation system, and we modeled it first as just a single enclosure, but then we rethought about it, and then we just remodeled it, having the CubeSat inside of it, and then that's why we came up with the second free body diagram that's on the right side. This, the way to find this, the way that we did to analyze this this frequency was that we just found the natural frequency of this system, of this enclosure, of this model, where we had to do, of course, natural frequency is K over M, right? But in this case, we have two Ks, which is the stiffness factors of the enclosure, the stiffness factor of the CubeSat, and the masses of the enclosure plus the mass of the CubeSat. This, again, pretty straightforward. It's just moments of inertia. And could you please move to the next page? Yeah, there. And in this one, it's just basically just finding the K, which is a factor of the modulus of inertia, moment of inertia, the modulus of elasticity, and just the length. Of course, the moment of inertia of the enclosure has to be taken as a hollow shell. So of course, you have to take the difference of those two dimensions, but the rest was pretty straightforward. This led to a 951.17 hertz, which is within the range of 800 to 8,000 hertz, which from, as what I said before, is from the SLS documentation, our system, and from our calculations, we can see that our system is complying with this range. Therefore, it also will also comply with 3,000 Gs. The fourth analyzed metric was the thermal expansion. Thermal expansion was done to ensure the enclosure must not expand less or equal to about 0.1% of the initial volume. We thought about this metric just because this percentage is not going to interfere. We calculated this percentage just to make sure that there is no interference if the component gets to expand. So of course we had to do this thermal expansion calculation. For the thermal expansion calculation, one of the things that we had to add to it was the coding, which is the solar white, right? It's just a regular thermal expansion function. The only thing that we just added, again, just the absorbance, which is the absorbance from the solar white. And this decreased this led to a 16.33 millimeter cube thermal expansion, which is about 0.08% difference from initial volume. just to clarify, the solar white was compared to other coatings, and the solar white was the best one, not only because it had greater properties compared to other ones, but it also had a flight heritage. So yeah, this was just the analysis for the thermal expansion. Just to summarize, the enclosure and mounting subsystem, we had very specific metrics. We just summarized them. We just summarized and put the most important ones here. And as you can see, we were able to we were successful in analyzing, calculating, designing to meet all these requirements. I'm just going to read the first four. Must withstand steady state structure loads at 10 Gs. So we were able to do it with a factor of safety of 1.285. Must withstand a shock response between 800 to 8,000 hertz, which is, we were able to do it at 951.17 hertz. And for example, fundamental mode frequencies at about 866 hertz, the thermal expansion, which was 0.08%, less than 0.1%, which was what we were calculating. And we were also able to get a mass that was around 58% of the total weight of the CSD, mass of the CSD, which it completely passes our customer need, which was less or equal to 60%. That so yeah, that summarizes the analysis that we did for the enclosure and the successful metrics that we were able to accomplish for this.
All right, so now I'll be talking about the opening door subsystem. All right, so this consists of a torsion spring door, the burn wire module, and some other smaller components. The idea is that it instantly releases the satellite and that it has additional redundancies and reliabilities built into it. Next slide, please. All right, so our primary concern was reliability, right? So we wanted to reduce the chances of failure, so we maximized as much simple mechanical systems, right? The electronic portion of it, the burn wire, is tensioned across a 400 denier Vectran cable, and it has additional redundancies built into it, and we'll talk about later. The satellite is passively pressed against the door, right, for all of flight. So the reaction force is translated from the structural rails of the CubeSat into the door. So the CubeSat itself is kept safe, but the structural rails is translating that load. The torsion springs are pre-tensioned so that they will assist in opening the door, and we'll talk more about that later. The burn wire also is tensioned inside the burn wire module with 4 separate springs for more redundancy. And the burn wire itself is wrapped around a nichrome cable, and there's basically 2 relays that can both independently work of each other. So in case one goes down, the other one can be used to increase the chances of success. Next slide, please. So we're going to talk more about the burn wire assembly. All right. So the burn wire assembly basically uses a hook to hold a notch in the door close. It is kept static by a 400 denier Vectran cable. So this Vectran cable is basically held in tension inside this assembly, and is also held across some nichrome wires. So the nichrome wires act as resistors, and when we put across a voltage and current across them, they get very hot. So our goal temperature was 400 degrees Celsius, so that would exceed the Vectran's melting temperature of 330 degrees. Using established tables on nichrome wire, we found that about 1.4 amps were needed on 30 American wire gauge nichrome. Using vehicles IR, we found that 1.1 volts required. Very, very doable. 1.1 volts and 1.4 amps. It's easy stuff. When I was at the summer of this internship, working at Sidus Space, I was personally working on projects with similar burn wire assemblies, and we had very similar results. And the estimated cut time is about 3.5 seconds, which also lines up with some of the literature that's out there on burn wire assemblies. Next slide, please. All right, so the opening door subsystem, opening time. So this is of importance, right? Because we want to get out of the way of the CubeSat as fast as possible while still being safe. So we're going to use 2 torsion springs that are built into the hinge to apply a torque to additionally spin it out of the way. All right, so that's the torque number there on the screen. And the opening door moment of inertia was also calculated. So we basically took the half length and then the weight, and then basically did an average and found the moment of inertia. We did an angular acceleration equation, torque divided by moment of inertia. Found the acceleration was a pretty fast 218 radians per second. So then we basically plugged all these numbers into a simulation that we set up, and basically made a coordinate system where we applied the acceleration of a CubeSat and then the acceleration of the opening door, and found where they conflicted or impacted each other. And so the door outpaces the satellite travel after 0.03 seconds, which means that there's a little bit of pushing, but that's okay. That's less than 20% of the acceleration path of that the CubeSat experiences. So most of that energy is still going to go into that launch. It's still going to launch at about 2.3, 2.2 meters a second. The door is fully out of the way at 0.085 seconds. So well even before the CubeSat is fully out of the CSD, the spring door is out of the way. All right, next slide, please. So in terms of how we handle the CubeSat, when it's contained, the satellite is pressed against the door for all of flight. The load-bearing rails inside the CubeSat are what contact the door, and the sensitive parts are still protected. Between the side panels, hinge, and the lack of a perfect door seal, there are no opportunities for gases to dangerously pool up and build up pressure. And there are also no compressed gases, no volatiles, no high voltages, no exotic launch methods used. Everything's like very simple mechanical stuff. And so basically we're making sure that the satellite remains safe. We're not playing around a fire near the CubeSat. And then the electrical and dynamic portions, right? So the hook that swings and the door that swings and the burn wire that gets burned is kept in a separate location. So it's not in the same payload bay. Next slide, please. All right, so a little bit about the forces on the door. So we approximate the door as a simply supported cantilever beam. And then the hinge and hook act as the 2 supports on the door there. So those 2 reaction forces. So the highest force concentration is where that notch has its thinnest cross section. That is a shear stress. And so that was calculated to be 2100 newtons across 80 millimeters of square area. So that gets a shear stress of 26.25 MPa, which is well below aluminum 6061 construction's shear of 201. Next slide, please. So the opening door subsystem, similar story. We just got a hook. It's also made of 6061. That notch force is now translating to the hook, 2100 newtons, and the smallest cross-section area of the hook, which is in the tensile orientation, is 60 millimeters squared. So the stress experience is 35 MPa, which is less than the yield of 661 aluminum of 241 MPa. The burn wire acts as a counterforce, and so what's required of it is about 850 newtons. So it basically acts as a lever because there's a 17 to 41 reduction ratio in between the hook, and that was another thing that was used at the internship, is that they used levers to reduce the load requirements on the Vectran cables. And so the Vectran 400 denier is rated for just over 2,100 newtons of force. So that is well in excess of the 850 newtons that's asked of it. Next slide, please. So let's go ahead and just check through all our customer needs. So the opening door must open up 100% reliability. When we did our calculations, we found that assuming that the electrical system has a 2% chance of failure and the mechanical systems have a 0.1% chance of failure, it has a 99.76% chance of reliability after you count the whole system in series. So essentially 100%, you're not going to really be able to obtain 100% in real life. There's always going to be a little bit of error. And so we figured that that was sufficiently close enough to 100%. The opening time must be less than 2 minutes. So in between the burning and the swing aside, it's essentially 3 seconds. The CSD must be able to depressurize in less than 2 minutes. We have basically no opportunities for gases to build up. So essentially it's going to be 0 seconds of depressurization. With the materials that the CubeSat team we worked with, the aerospace team gave us, they had hardly any outgassing to begin with. The internal pressure of the CSD is less than atmosphere, which is true. We do not have any compressed gases or any other gases going on in the environment. It must be able to withstand 2100 newtons of applied force at the door, and it could withstand well in excess of that. And additionally, it can withstand those steady state loads, which it can also exceed that load requirement by a severe margin. All right, I'm going to go ahead and pass this off to Shadar. You got the floor, man.
Okay, next up is the dispenser subsystem. The primary focus of this system is to eject the CubeSat within the CSD at our customer needs velocity, and do so without adding any pitch or yaw moments. So this system contains of three major components: and a 661 aluminum backing plate fastened into the greater CSD, an aluminum push plate that slides on the guide rails that's responsible for pushing the CSD out of, that's responsible for pushing the CubeSat out of our CSD, and a steel compression spring that's bimetal welded into the base plate, and the push spring that acts as the primary force motivator. The CubeSat is spring-loaded into the assembly with 333 newtons of force, and on ejection, the system launches the CubeSat out at 2 meters per second, which is our customer needs required velocity. So to accurately select the spring to expel the CubeSat at this velocity, we started by determining the required spring stiffness. This is determined from an energy balance within the system, where the kinetic energy of the CubeSat in motion is equivalent to the spring potential energy. The kinetic energy was determined from our customer needs statement of 2 meters per second and ended up being 20 joules. And the spring potential energy was determined from the maximum compression distance of 0.3 meters. Equating both these values and expressions and solving for stiffness, our desired spring stiffness was about 1,111 newtons per meter, and the corresponding spring force was 333 newtons. From here, we selected our spring from a commercially available retailer to be 7-gauge music wire with a 158 millimeter free length and an outer diameter of 69.44 millimeters. To accurately determine the stress and deflection of the base plate, which takes most of the spring load, we decided to model it as a rectangular plate with a centralized concentrated load. The stress in this plate can be expressed as a function of spring force, plate geometry, Poisson's ratio, and the deflection is determined as a function of plate geometry and modulus. The maximum stress in our plate is 36.22 megapascals, which ends up giving us a yield factor of safety of 7.6, and our maximum deflection is 0.06 centimeters. These values ensure that our design satisfies all structural integrity requirements and that the system does not fracture and cause debris egress. So to go through all our customer needs, we must lose less than 1% of the CSD in ejection because of the fact that we have no predicted failure with a good margin factor of safety in our design. We estimate that we'll lose less than 0.001% of mass. We must use materials that outgas less than 0.1% of their mass. No materials in our dispensing system outgas any mass. The CubeSat ejection velocity should be between 0.5 and 2 meters per second. At our spring rates, our velocity is 2 meters per second. The center of gravity cannot have an offset of greater than 1 centimeter. And because of the fact that we have a fully symmetric dispensing system, we have 0 centimeter center of gravity offset. The CSD must survive in mission operation state for 2 hours, and our dispensing system is capable of surviving all loads for 21 days in emission state. And with that, I will pass it on.
This section will cover the infrastructure subsystem of the CSD. In the rendering, it can be seen that all the electronics and communication equipment are housed in a monopiece shell that will be fastened to the bottom of the main enclosure, sealing the infrastructure from the elements. The wires aren't shown to reduce clutter in the rendering, but there is a small mouse hole for the wires to be routed through to reach the burn wire mechanism, and those wires will be covered by a wire protection panel as well. All infrastructure equipment is fastened to the bottom of the enclosure with spacers, as you can see below. Next slide. The main purpose of the infrastructure subsystem is to power the CSD components and help the CSD communicate with NASA ground control. This is achieved mostly by these 3 points: provide power to the onboard Raspberry Pi Zero, provide power to onboard sensors and burn wire heaters, and communicate with ground control via X-band patch antenna. If infrastructure subsystems can do these three things well, then the chances of a successful mission increase greatly.
So the infrastructure subsystem itself was split into 2 parts, power and communication. The power section is only to power the onboard systems for the CSD, those systems being the burn wire antenna, or the burn wire assembly and the X-band antenna, along with 2 limit switches that are used to ensure that the door is opened. So we have a circuit diagram below here that shows the Raspberry Pi circuit, which is running off of a 2S 18650 LiPo battery cell, running through a voltage regulator to make sure it's feeding the Raspberry Pi at its necessary 5 volts. And the Raspberry Pi communicates with the 2 limit switches to ensure the door opens, the 2 relays, which run the primary burn wire assembly and the backup burn wire assembly, and our EnduroSat X-band antenna to communicate back with NASA. The second circuit is only running the burn wire assemblies to make sure that the burn wire assemblies have their own power supply that isn't affected by any other part of the system. This is a single 1S 18650 LiPo battery cell, again, running through a voltage regulator to ensure that it's running at that 1.1 volts that Zach had found earlier for the burn wire assembly. If in any situation the first burn wire assembly does not work, the Raspberry Pi will recognize that with the limit switches built into the door and will engage the second burn wire assembly to ensure that the door will open. So just to go through why these were chosen, or each battery cell, again, they're just single 18650 LiPo battery cells. The only reason that there's a 2S is to ensure that the Raspberry Pi has enough voltage, as each 18650 cell only provides 3.7 volts. We're using LM2596 Texas Instruments buck converters for our voltage regulators. These have flight heritage and have the necessary parameters to change our voltage down to what we need. One of these is set to 1.1 volts, as we said before, and the second one is set to 5 volts to ensure the Raspberry Pi doesn't get very expensive. The power draw for this whole system is very minimal. The Raspberry Pi at most pulls 230 milliamps for the 3 hours maximum for the mission. And the burn wire will only run for 60 seconds at maximum, but it should cut within 3 seconds. This is only running at 1.4 amps at 0.0233 milliamp hours. This means that the maximum draw, which is on the burn wire circuit, is at 1.4 amps. These batteries are capable of providing far more than that. And the total mission draw for both packs is 700 milliamp hours, but each battery cell holds 3000 milliamp hours. So we're able to account for any charge loss due to poor charging techniques or due to temperature fluctuations that can affect battery capacities. Throw it back to Asher here.
Yeah. The communication subsystem is tasked with communicating with the NASA Deep Space Network and controlling all the electrical interfaces within the power subsystem. The communication system has to start with the EnduroSat X-band patch antenna. The patch antenna is an antenna that operates between 8 to 8.4 gigahertz, which fits within the 8 to 12 gigahertz X-band range for NASA's Deep Space Network. The antenna will receive the signal from NASA ground control, letting the CSD know it's time to deploy the CubeSat. This is why the patch antenna will be wired to the Raspberry Pi Zero. The Raspberry Pi Zero serves as the onboard computer for the CSD, making sure electrical signals are sent properly. The deployment signal received by the antenna will be read by the Raspberry Pi. The Raspberry Pi will send the current to the burn wire system to release the door. Since the communication system is the trigger to the whole CSD deployment, it's imperative that it works. For this reason, flight heritage has been prioritized for this subsystem. The EnduroSat antenna has NASA flight heritage, and the Raspberry Pi has been shown to work in space as it has been used in many space experiments. The 2 components also have the benefit of being low profile. They don't take up much mass or space from other components of the CSD, making the design more flexible. And that's it.
So just to run through to make sure we're hitting our customer needs, we have, since the circuit is standalone, it's grounded to itself. so that hits this this customer need here. The X-band patch antenna communicates within the 8 to 12 gigahertz signal that is necessary, and also can communicate with NASA's deep space network. The energy storage device with a capacity of 3,000 milliamp hours is exactly what we have. And the electrical conductivity must have a surface resistivity of very low. Everything we're using is within that realm. And from here, we'll go to the key design highlights with Zane.
Yeah, so just like a brief overview of some things that set us apart. So all of our components have, or a lot of our components have flight heritage, so successful space missions. As my teammates were explaining, Raspberry Pi, burn wire release system, they're all tried and true techniques as far as NASA's flight standards. Advanced manufacturing methods that we could use in production, those would really tighten tolerances since we would use processes like wire EDM and CNCing. And finally, our infrastructure components have relatively low costs, and that helps us increase our margins and allow us to prototype using exact production level electronics. So just like an overview of the prototype cost, we're at about 78% off the shelf components at around $400, and 22% is raw materials at around $100. And then we'll go into the production cost. As you can see, a lot of our production cost involves labor. So between design labor, manufacturing labor, and assembly labor, the breakdown is shown on the left, and that accounts for 72% of our total budget. Testing and quality, we really wanted to make sure that we validate this product. So as you can see, 25, almost 26% of our budget is allocated for that. The remaining 2% is off the shelf components and raw materials.
So the design prototype does, it's mostly made up of easily manufactured 3D printed components and standardized fasteners for ease of manufacturing and assembly. But it does represent the greater production line CFD, and for that reason, it will have a mock-up burn wire system and Raspberry Pi for communications, as well as representative 18650 battery cells for power.
So as this design was evolving, a communication gap grew between our team and the Aero design team that was leading the CubeSat design itself. And this communication gap led to a difference in design goals, specifically in outer dimensions and in power plug pass-through. Specifically, the outer dimensions, there was a miscommunication with what exactly the outer bounding box was for the dimensions of the CubeSat itself. And this led to a difference in design that causes a conflict. The other issue with the power plug was there was a confusion in between whether or not the CubeSat needed pass-through power. And we're going to address this, first of all, by keeping more clear open lines of communication with any CubeSat provider that we work with. The outer dimension can be fixed either by expanding the enclosure or changing the CubeSat design, or a combination of both to ensure that neither team is put under too much undue stress. The power plug pass-through is actually a advantage, as most commercial CSD providers currently have the power plug pass-through as an option. And as we already have a complete and validated design without the power plug pass-through, creating another one with it and revalidating it shouldn't be too much work, as all you need to do is integrate with the SLS power, make sure you have proper voltage step downs, and ensure that there's a consensus on the location of the power plug.
This brings us to our conclusion. Our team has used its extensive experience to design Jack in the Box, a reliable CSD solution that meets all necessary customer needs. Customer needs can be shown in the design. The CSD ejects the CubeSat at 1.9 meters per second by opening its door and using a torsion spring latch released by a double redundant burn wire system. We made sure that our design had flight heritage and is backed by engineering calculations, as you saw in the previous slides. And with a final production cost of $377,000 and $937 and a prototype cost of $495, the design is fiscally feasible and would maximize profit per customer, as we stated before. And that's the conclusion to our presentation.
Awesome. Thanks, guys. Okay, so we did start a little bit late because I was fumbling around with the grading rubric. So just as a quick follow up to that, I did send the grading rubric through chat for our panelists, and we're going to do something slightly different this year, which is instead of just giving you guys all the rubrics at once, we're going to do them one at a time. So if you just fill out this one and send it to me as soon as you're done, that's how we'll manage it this time around. So are there any questions from the panelists? And sorry, I'm having two thoughts at the same time. So one was the explanation of the rubrics, and the other one was we started a little bit late, so we could probably run for about 10 more minutes because we want to give these guys a full set of questions. So any questions for the panelists?
I'm actually going to start if that's okay, because I was supposed to be in another meeting 20 minutes ago. So
Yeah. Oh no, sorry. Go ahead.
that's okay. Can you guys go back to your second cost slide, not the prototype one? Yeah. Okay, so there's a couple things here that I want to ask about. So did you guys account for shipping costs?
Yes. So all of our raw material, all of the costs there for OTS parts and raw materials, that includes shipping in there, whether that's from any of our vendors. So that's factored in rather than having a separate cost category for that.
Right, but what about shipping to the test site?
That would be within the testing and quality, since some of the testing would also happen at site.
As an investor looking at this, if you told me that your transportation cost to the launch site of the finished product falls under testing and quality, I would say you're blowing smoke. So I will choose to believe that that is accurate, that is where you put that, but in the future, definitely don't put that there, because that doesn't qualify under that. What about your own salaries? Where are you putting those in here?
Mm-hmm. That's accounted for in design labor. So we, as design engineers, we assumed a $75,000 per year salary, and that's 6 engineers for the 6-month production. And we also hired an electrical engineer contractor to help with some of the infrastructure components. So that's also included in design labor.
Okay, so you said that was $75K per month?
That's an annual salary. So cut that in half for 6 months and times 6.
7.5
yeah.
times 6 people. I'm assuming I don't do math. Does that work out to 265?
And then if you add a $40,000 electrical engineering contract, it comes out to 265,000.
Okay. And then what about y'all's profit margin?
I'm sorry.
Because if you look at customer need 25, it says the production cost budget must also indicate the subcontractor's profit margin.
Mm-hmm. Yeah, so we assume that our total budget allocated would be the 500,000. So any difference between the 500,000 that we are provided and the 377,936 would be our profit.
Be very careful with that. Just because you're awarded a contract for $500 doesn't mean they're going to write you a check for $500,000 and say, go. You don't necessarily get the leftover money. Because if I give you $500,000 and I say, what's your profit margin? And you come back and say, our profit margin was 50%. That's saying, okay, you took $250,000 to do all the costs and do all of that, and then you're keeping $250,000. Like, that's a pretty large profit margin. And I'm going to start being like, whoa, hold up. Maybe I shouldn't give you guys $500,000 because you don't need that much to do it. So definitely, especially since, and the only reason I'm kind of really picking on that is because it specifically says in the customer need, indicate the subcontractor's profit margin. So just moving forward, I know it's little, I know it's the tweaks, but just kind of be aware if they specifically ask for that. And again, coming from an investor side, if I'm saying, even if I didn't say what is your profit margin, I'm going to want to know that answer. That's just kind of a standard run-of-the-mill business. You know, think about it. You like, okay, I'm going to Disney World and I'm paying $7 for a soda. Like, that's ridiculous. And so what do you say? You're like, they're making like $6.98 off of me. You know, that's their profit margin, or enter percentages, whatever that works out to be. Go to the next slide real quick. The low cost ABS 3D printing for several components. So you have an outside company you're reaching to do those printing, or how does that work?
Go ahead, Trita.
Yeah, so as part of our prototype cost, we accounted for the cost of the spools of filament that we'd use to manufacture it. If that's what you're asking.
Right, but where are you planning on using the UF, the lab there, or do you have a outside company that you're going to go rent their space to do the 3D printing? Like, where is it actually happening?
Right. So yeah, the assumption that we made here was that we'd use the UF lab, where we'd only really have to, where we'd have access to 3D printers, and we'd really have to bear the cost of the filament.
Okay, and would that be for the prototyping, or would that be for all production in the future?
That would just be for the prototyping.
Okay, so for the future production, you have an outside spot, space, whatever you want to say, company.
Yes. So
Okay.
all manufacturing for the production line model is outsourced to professional manufacturers.
Okay. I will leave that part in Dr. Trum's court. If you were not a student group, if you would be able to use the printers for prototyping. So I'm going to assume yes for my lack of knowledge, but someone can come in and correct me if needed. The other two things, so that's all the questions that I have. So you guys survived the grilling portion. Good job. So my other two comments is thank you for the love of all that is good in this world. Thank you at the very beginning telling me why you are qualified. Because if you just started in straight with, you know, hey, we're senior engineers and we can do this, like, that's great, you're senior engineers, but okay, are you a senior engineer in, I don't know, marine sciences, something or another? So kind of really going more into, hey, we've had internships and we've done this and that, made me go, okay, they probably know what they are talking about, which, as you saw, led into my questioning, saying, I'm going to trust that you guys know what you're saying here, because you made me build that trust at the beginning of the presentation. So fantastic job on that. And then second, you all look incredibly professional. You all have the same background. You all spoke quite well. You have no idea how much that truly plays into an investor's confidence, into whether or not we want to buy your product and or believe in you guys. You know, again, there's been a couple things I'm like, I'm just gonna believe that's right. You know, part of it again falls into you fake it till you make it. You know, it looks like you know what you're talking about. Your background, you're all dressed nicely. You spoke with confidence. A+ on those two things, and that's it for me. Fantastic job, guys. You really did impress me, which, believe me, is not something you hear very often coming out of my mouth with these presentations. So good job. I'm jumping off to another meeting.
All right. Thanks, Julia.
Thank you so much.
Thank you very much.
Okay. So we've got just maybe a few more minutes. So do we have any other comments from Sydney or Elise or Aditya?
No comments
Hi.
from me.
Oh, sorry.
Sorry. Hi, this is Elise from Cummins. Yeah, great job. I really like your team name. Very nice. And you had really good communication skills, and I liked your visuals and going through all the hand calculations with your assumptions. That was really nice. And you also identified your communication gaps. We know that system integration is really important, especially with working with different teams like an aerospace team. So it's really important to have clear and good communication. So I think that's definitely an area for improvement. Kind of on that note, did you ask the Aero team about any? I watched a couple of their presentations last week, and they had this foam that I mentioned for dampening vibrations and insulation. Did you ask them about that at all? And did you consider that in your vibration calculations?
I think this falls underneath the rails design, as there was a mention of putting a foam or rubber insulator to limit their vibration. Believe that was under Alejandro's system.
Yeah. So in the assumption that we calculated, we didn't really account for the vibration, but we did account it in terms of design wise. We sort of like added as an add-on to a final design, right? If the company wants to add it on, just like an initial, like an external dampener to reduce those vibrations. But yeah, well, we didn't really show it in the slides. Yeah.
Okay, thanks. Yeah, another thing was, I think you calculated the maximum temperature was 342 C, was that right? And that was just from the sun's radiation onto the solar coating.
Yes.
Was that acceptable to the Aero team? I know they probably have some like camera equipment and everything that is pretty critical.
Well, our temperature is a little more of the limits of what they wanted. Basically, what they wanted, if I'm not wrong, was from a range of -32 Celsius to 300, I think, Celsius, and we're going from -45 to 347. That's where that temperature comes from, though. So yeah, our requirement basically exceeds their requirement, so they will be safe.
Wait, didn't you say it was outside of their bounds?
Yeah, like we just, how can you say that? We
what we expected to experience was higher.
Yeah, higher.
Designed ours to survive what the SLS mission planner's guide said was the maximum temperature, and then what they said theirs was going to experience was higher than what we designed, or was lower than what we designed this for. This change in temperature is from I think it was 660 degrees from the
it's just the one you see above. Yeah, it's just from the SLS.
So this is change in temperature is from it's from the external to internal.
Yeah. But yeah, in this case, it's just again what Jack said. We just like calculated. We calculated an value or a temperature that was gonna be higher than what they wanted. So therefore, our radiation shouldn't be, or our thermal expansion radiation shouldn't be as high, or shouldn't affect the CubeSat.
Are you talking about, I'm sorry, I thought they want to minimize the temperature so that their camera equipment isn't damaged, or any other components.
Oh, I think I know what you mean.
Like maximum temperature of the camera?
Yeah, I'm sorry. I think I understood I understood you wrong. No, yeah. This is within limits of what they wanted. Because their components required us to be within this range. So we assume that range, and we should be that. So like all our components are basically, they're very similar. Like even if our materials and the coding is just gonna aid very similar to the ones that the aerospace team is using. So we should be within. We should be able to not do any damage to any electrical components to the CubeSat.
Okay, thanks.
Okay, probably time for one more question, because as I said, we ran a little bit late when we started because I was still getting my stuff together. So any questions from let's see who's left, Sydney or Aditya?
I guess my only question for you guys is, so depending on your electronic or control subsystem, how are you guys going to insulate it from any type of radiation or arcing or anything like that?
So the enclosure on the rear that the infrastructure is held in is also painted with that thermal white to protect it from any thermal. As for radiation, Raspberry Pi has been tested by the University of Utah with full exposure in space and has been rated to survive for over 300 hours, which is a very impressive feat of engineering for the Raspberry Pi team. As for any of the other components, all of them are within the temperature or will work within the temperature bounds of living in an enclosed capsule in outer space. As for arcing, I'm not sure what you mean.
Like, how are you insulating all your components? So
they're all on standoffs off of the enclosure, so they're not communicating at all or running any current through the actual enclosure itself. And then all of the wires are using grounded shields on them as well.
okay, so you're protecting it from internal noise as well from each of your components to each other.
Yeah, so they're laid out. Run it back to the photo. They're laid out as far away from each other as they can be. These two relays shouldn't, or relays are usually put pretty close to each other. They don't interfere too much. As for the voltage regulators, those can interfere with each other. So they're put apart, put far enough apart that they should not interfere. And the Raspberry and antenna are put as far away as we could get them from the relays and from the voltage regulators so that they're not interfering with them at all.
Well, you also have power line noise. So are you shielding all your power lines as well?
Yeah, that's what will have the grounded shielded wires.
And for your relays, again, my expertise is in electronic systems or expertise.
Part of the reason we said we were going to hire an electrical engineer is to review the system, as our specialty is not electronics.
So those relays, generally mechanical relays, they have a high failure point in general. So this is just a suggestion. So maybe moving to something like solid state relays might be better.
Yeah, MOSFET relays was one of the goals for the electrical engineer that we would hire. Either that or putting all of this onto a single circuit board, as the LM2596 chip that I mentioned is just the single chip on these blue boards. Everything else on the board is sort of an add-on. For example, the small blue box is how you adjust it, but an electrical engineer should be able to put almost all of these components onto a single custom circuit board to minimize space too.
Okay. Yeah, that's all I have. So.
Okay, and good timing, because the next presentation actually starts in 1 minute. So we wrapped up with perfect time. So okay, well, so with that, we'll close things off for this group. I want to thank you guys for sharing your presentation with us. and especially for volunteering to go first. That's sometimes a nerve-wracking decision to make. It's you sort of get it out of the way, but also you know, you're the guinea pig. So I appreciate you guys volunteering to do that. So I think that's all we want to say. So we'll leave you guys the room if you want to debrief. But great design, and look forward to hopefully building this or something close to it in Mech 3.
Thank you, guys.
Thank you, Professor.
Thank you,
Thank
Professor.
you.
Thank you so much.
Thank you very much.
All right,
Thanks,
we'll
guys.
we'll see you.